All right, so we're going to start with number 4 here. So I should make this a little bit bigger. All right, so we've got this person on a rocket traveling at this with respect to the Earth. And then they see a meteor come behind and pass her. Speed as she measures of this. How fast is the meteor moving with respect to the Earth? So, how many different frames of reference do we have here? Anybody? Three, but good try. Good. Three different frames of reference. So this is number 4, and right away we should note that we have 3 frames of reference. The 3 are: we have the ship, we have the Earth, and we have the meteor. Which one are we going to take as the stationary frame of reference? Okay, we'll do it for the Earth. And that's good because I think they ask us how fast is the meteor moving with respect to the Earth. So it's good to take the Earth as the fixed one. Oh, I forgot to have our equation sheet. Let me get that open so quick. Let's see. So, all right, there we go. And so, see, what else do we need here in our y? How about the speed of light is constant and absolute? From all frames of reference. I think it's important to remember that absolute part, especially when we're dealing with relative velocities, because if we get an answer greater than c, we're in trouble. All right? And I would also put in here that velocity is relative to your frame of reference. All right? So there's nothing absolute about velocity except that you can't exceed the speed of light. So equation-wise, let's see. I need my relativistic velocity equation. And then I can make that smaller, put that here. It's important to remember that things like anything with a prime, so whatever you have with a prime, is from the ship's frame of reference, and anything without a prime is the Earth's frame of reference. So it's good to note that, because the biggest mathematical problem usually is substituting in incorrectly. So our U's are going to be the meteor. The V's will be the ship, and Now it's just making sure that we put in the correct things in the correct places. We're looking for the speed of the meteor with respect to the Earth, so that would be u. The speed of the meteor with respect to the ship, which is u prime here, is 0.45 c. So 0.45 c plus the speed of the ship with respect to the Earth, that's at v, which is going to be 0.55 c for me. All these numbers, of course, will be different for you. Over 1 plus 0.45 c times 0.55 c, forgot my 0 there, over c squared. Now, mathematically, if you look, they want the speed in terms of c. So what I really want to solve for is not u, but u over c. Remember, if I have u over c, that's equivalent to the coefficient. So, in other words, what I'm saying is, if I find u in terms of c, I'll have some number n times c. If I solve for u over c, that will give me the number n, which is what I'm interested in. What percentage, what part of the speed of light is u? So what I would do mathematically first here is I would, well, first thing I'd do is I'd cancel out these c's, and then I would factor a c out of the top, so I'd end up with u over c is 0.45 plus 0.55 over 1 plus 0.45 times 0.55. And then I would solve for u over c. And that will give me the coefficient that would go in front of the speed of light to tell me what u is. All right, but factoring out that c, I never have to deal with what is the speed of light. Let me know if you need help individually on any of that. And then we'll go on to the next one. All right, so we're going to do number 5. And number 5 gets slightly trickier in that the ships are moving in opposite directions. And you do need to take that into account. Even though there's not vector symbols on our equation, we do need to take the directionality into account. They should be vector symbols there. And we're looking for the velocity of ship 1 relative to ship 2, and the velocity of ship 2 relative to ship 1. Shouldn't that be the same speed, just opposite in direction? I mean, if I'm sitting here and I don't know, Emily is running away from me, whatever speed I see her moving at, from her frame of reference, isn't that the speed I'm moving at? Yeah, but opposite in direction. So my answers for A and B are going to be the same magnitude, but opposite directionality. All right. So let's go for velocity. So that would be good to note right here in your Y in 5. When switching between frames of reference, velocities are equal in magnitude, but opposite direction. And then we should go with our boilerplate of C is constant and absolute in all frames of reference. All right, that's probably sufficient for the y. Let's grab our equation again. Again, we're going to take non-prime as Earth, and we will take prime, let's see, velocity of ship 1 relative to ship 2. So we will take anything with a prime as ship 2, as measured from ship's 2 frame of reference. So, and that's what they mean here, the problem with choose the Earth for the S frame. S stands for stationary, or can be interpreted as stationary. And the spaceship 2 as the S prime frame. Use sign your answer to indicate direction. So, they leave Earth in opposite directions. So we're going to take doesn't really tell us which one is which, but so I'm going to do a little drawing here. Let's see. Here's my Earth. We have ship 1, and we have ship 2. Whoops. Not drawing very good ships this morning. Must be Friday. And both these are moving at 0.52 C. 0.52 C. Let's take this direction as negative. All right, so we'll say that one's moving at negative 0.52 C. Both of these in the Earth's frame of reference, right? So what we have here, inputting our equation, I'm going to rewrite our equation and just say this view is for ship number 1, and that's from the Earth. So U prime is ship number 1, V is ship number 2. So just as a reminder to myself, alright, as I work my way down here. So I have U1, that's negative 0.52 C. That equals, oh, I forgot the plus up here, didn't I? Sorry. Thank you. Negative 0.52 C plus 0.52 C. Well, that can't be right. Oh, this one, I don't know this one, do I? That's the problem. This we're going to leave as U prime, because that's the speed of ship number 1 as measured from ship number 2. 1 plus U prime 1 times 0.52 C over C squared. Set the page. Again, now I need to solve for U1 prime. I'd rather solve for U1 prime over C, since they asked for the answer in terms of C. So I'm going to do a little bit of finagling. I'm going to divide both sides by C. And that will give me, like here, it'll give me negative 0.52. Is what I'm doing is I'm dividing this by C. And then if I divide this side by C, that's like putting a C here and a C here. So that will equal U1 prime over C plus 0.52. And then on the bottom, I'm going to get 1 plus and this C, one of the C's cancels with that C, the other one stays under here. So I have U1 prime over C multiplied by 0.52. I'm just going to parentheses that. So now I can use Wolfram or some other solver or my calculator to solve for U over C. And that will give me my answer. All right. You guys want to walk through how to use Wolfram to solve this? Yeah, would that be useful? Okay. I'll use Wolfram. I just need to go over type. The U over C I'm going to put in as the variable. What's everyone's favorite variable for today? Oh, come on. We always do X. Q. Q? Q. You got it. We'll do Q. All right. So I'm actually going to pull this over to the side so I can see. Q. Now. And so I'm going to put in negative 0.52 equals Q plus 0.52 divided by, oh, and I'm going to put parentheses around that top part so it does it correctly. Parentheses, 1 plus Q times 0.52. Close. See if that interprets that correctly. Looks good. So it interpreted it correctly. And I get an answer of negative 0.818, which is pretty good. That's what I would expect a negative answer, right? Because I would expect it would see ship 1 moving to the right. So let me pause it and we'll check and see if that's right. So we're going on to number 8, another relative velocity one, where we have a missile that's shot from one spaceship to the other. Towards the other, it leaves the first at this and approaches the other at this. What is the relative velocity of the two ships? The y for this is going to be very similar to what we just did, right? We've got 3 frames of reference, and we got to pick one of them as a stationary frame. I'm going to start off with a little drawing, because I think sometimes we forget to picture these things. And so we'll have the first ship. We'll make it a Borg ship. How about that? Good old Borg cube. And it's moving this way. And the other ship. Did they say approaching each other? Yeah, so they don't say. So what do we want to say? We'll make the other ship a circle ship. Do we think they're moving towards each other, or like one's chasing the other? We'll do chasing. Okay. And this will be our square ship and our circle ship, and then we have the missile here. And let's see, missile is shot from one spaceship towards the other. It leaves the first at point towards the other. Oh, okay, so as viewed from the velocity of the missile, this is always good to get down. Which one do you want to say is the stationary one? We'll say the first one. We'll say the square one, our square ship. So we're saying that our square ship is stationary. And you'd probably also put that in your y. All right, but the y is going to be almost identical to the previous one. So that means that that is the ones without the primes. So the ones with prime are from the circle ship. Is moving. All right, and this is going to be u or u prime. The movement of the missile is going to be the variable u, where the movement of the circle ship will be variable v. All right. So we grab our equation. And bigger, and we start substituting in. So u would be the speed of the missile from S, and they tell us if S is the one that fired it, it leaves at 0.9 c. So u for me is 0.9 c. U prime is how fast it's measured as moving from the other ship, which is 0.74. So 0.74 c plus, I don't know how fast v is, the ship is moving, so that's v, 1 plus 0.74 c times v over c squared. Oh, I love it when I just get one variable. Am I going to solve for v or solve for v over c? Solve for v over c. Yep. Because they asked me for my velocity in terms of c. So rather than finding my velocity, v, and then saying, well, I need what v is in terms of c, if I solve for v over c, I just get the coefficient in front of c. And most of the times it's going to be easier math, because now to solve for v over c, I just need to do the trick I did last time of dividing both sides by c, and then solving it for v over c. So give it a try, folks. Call me over if you need help. I will double check that our method worked. And then we'll move on from there. Just 1 second, I'll make the pause. All right, folks, we're going to hit number 3 here. Hopefully get a bunch of it done before the block ends. Then this one, it's good to do this one because it's not a relative velocity one like the other ones we've done there in the block. So you've got this star. It's 10.5 light years away. Remember, light years is a distance. A lot of people look at it and see the word years and think time. No, it's the distance light travels in 1 year. So it's a distance. How long would it take a spaceship traveling this to reach the star from Earth, as measured from the following locations? So, on Earth, how many years? On the spacecraft, how many years? We know that time is passing differently on the Earth than on the spacecraft. And we also know that on the spacecraft, they're not moving. The star is coming to them, and therefore the space between them and the star, since it's moving, is going to be contracted. That's why. That's one of the reasons it's not a paradox for less time to pass on the ship. They don't move as far, so it takes less time to get there from the ship's frame of reference. Otherwise, we'd set up some type of paradox where it couldn't happen. What will the spacecraft compute their speed to be from the results of B and C? In that, since B and C are both measured in the spacecraft's frame of reference, they're going to compute just using our normal kinematics in that same frame of reference. So let's see what we can get through. You guys okay with that? Those ideas being your why and me not having to write it? Yes? We're good? Excellent. All right. So we'll start right in on the how. And we are going to, this is number 3. And I'll just put C audio. It's kind of good too. Equation-wise, we are going to need our good old friend, the Lorentz contraction. And then we're looking at both time and length changing. So we'll grab this. Okay. And our approach can be, let's take it from the Earth's frame of reference. So in the Earth's frame of reference, we're going to also need, it's way back there in our equation sheets, all the way back to the first box. I'm going to just grab the definition of velocity or speed. Remember how I said don't forget anything? So from the Earth's frame of reference, this is from the Earth, they are traveling at 0.87 c. So their velocity is 0.87 c. I'm using this equation here, by the way. The distance they travel is 10.5. Yeah. Is 10.5 light years. And we're looking for the time it takes. Unit-wise, one definition I'm going to use is 1 light year equals, if you're traveling at the speed of light, 1c for 1 year. All right, so 1 light year is c years. So if I rearrange this for t, I get t equals 10.5 c times years over 0.87 c. My c's cancel out, and I find a time of 10.5 divided by 0.87. And I get a time of 12.1 years. So that's how long it takes me from the Earth's frame of reference as I'm watching for them to reach this planet, this star. From the ship's frame of reference, though, I'm going to move these down and over so I can keep using them. From the ship's frame of reference, less than 12.1 years passes, of course. I'm going to use that time on the ship. Let's see. I have to remember always t is greater than t naught, right? So this will be the Earth and this will be the ship, right? So time on the Earth equals time on the ship over the square root of 1 minus v squared over c quantity squared. So 12.1 years equals the time that passes on the ship over the square root of 1 minus 0.87 C over C quantity squared. And I get the time that passes on the ship. Let's see, it would be that times square root of 1 minus 0.87 squared. And on the ship, only 5.95 years pass. Right? I know I'm going quick. I just want to get it all down so that if you don't get it, if you watch it and you can copy it down later and follow along later. So now, but how far have they moved in that 5.95 years? I'm going to use my L equals L naught over gamma. And in this, L is always less than L naught. And so L is from the ship's frame of reference, and L naught is going to be from the Earth's frame of reference, because length contracts. So I want to know how far they see from the ship. L naught is going to be my 10. Oops, sorry, I'm going to switch colors. L over L naught over gamma. So L is from the ship's frame reference. L naught is my 10.5 light years. Gamma, when I divide by gamma, it's like multiplying by the denominator. So 1 minus 0.87 C over C quantity squared. So the amount of the distance from that the ship actually measures its travel is, let's see, 10.5 square root of 1 minus 0.87 squared. Oops. Missed that minus. Second insert minus. Enter. 5.18. Light years. And then for my final part, again, I'm going to use that V equals D over T. Their velocity is going to be 5.18 C years over 5.95 years. And I can do that in my head. I'm going to come up with 0.87 C. Hopefully. Hopefully. All right, let me know if you need help individually. I'm going to save and publish these. We're running out of class time.